Okay, so apologies for that. I'd just like to introduce our speaker today. Gregor Tanner obtained a diploma in physics in 1989, followed by a PhD in theoretical physics in 1992, both from the University of Freiburg in Germany. He then worked as a postdoctoral fellow at the Bohr Institute in Denmark, followed by 2 years at the UK as a research fellow at Hewlett, Packard Laboratories in Bristol. Gregor joined the School of Mathematical Sciences at the University of Nottingham in 1998 and became a Professor of Applied Mathematics in 2016. Today, Professor Tanner will provide an introductory overview and discuss applications to vehicle body vibro-acoustics and turbulent boundary layer excitation informant, or MBH simulations.
All right.
Over to you.
Thanks a lot, Jack. Yeah, thanks for inviting me. It was a bit stressful at the end. Broke down train. So yeah, but you just made it in time. Yeah, good to see some of your faces from maths as well. So this is more I guess, for a very engineering-inspired talk. So very little maths and apologies in advance, but we can maybe discuss later. All right, so this is the kind of technique we have been developing in Nottingham over the last, now maybe almost 15 years, called Dynamical Energy Analysis. It's inspired by a technique which is called statistical energy analysis, but it's sort of extending that. And there are lots of people I could list here which I've collaborated over the years. Very influential was the collaboration with Yanman. It's a tractor or diesel engine manufacturer in Japan. It's Satoshi Morita, and he has left the company since. Timo Hartmann was very good in writing the software package. So he's also left the university by now. And then the people I'm working with, this is Martin Richter in Nottingham, David Chappell, who was a postdoc at some point with me, but is now in Nottingham Trent University, and Joshua Frieden is a PhD student in boundary layer excitation work. Yeah, maybe put this all up here. So we're talking about structural vibrations, structural excitations, NVH, essentially. So not so much acoustics in this talk. I know, of course, this is here the mecca of acoustics, but it's sort of obviously related. You all know that one way of looking at structures experimentally, you essentially excite them. You do frequency response analysis. You get certain peaks giving you modes. You may do something like transfer path analysis, and then that gives you a way of looking at the structure. From the modeling side, the standard tool is, of course, finite element method when you look at structures. So you have meshes, but of course, I'm sure you're aware of that as well. With frequency, essentially, you have to go to finite meshes, and at some point, you have a limitation that the meshes just become too fine, and that's actually surprisingly low. I mean, I guess maybe 500 hertz for a car as this critical frequency where the models are just becoming too big. Okay, I guess we'll push that higher now. But as the structure itself increases, this critical frequency decreases. So if you're looking at ships, and I'm thinking, these big tank ships, or then this can be as low as 15 hertz if you think about this. If you then go to sort of high frequency methods, high frequency meaning being sort of above that cutoff frequency for a fired element, you have sort of the next best method is kind of ray or energy tracing. That is something people do in acoustics a lot, not so much on structures, because if you think about how would you follow a ray on the structure, which can be quite complicated. Often it's 2D. Sometimes, of course, you have to treat it as 3D. So that is sort of, that's where we come in. We think we can do this, but not with the standard ray tracing. We do this, what we call these energy tracing methods, or energy methods on structures. If you go to sort of the standard high frequency method in structural acoustic, structural vibrations is this statistical energy analysis. And I will talk briefly about that. That's essentially a power balance type method. So here you have very coarse meshes, they call them substructures, but then it's very critical on how you do this substructuring, whether that actually works or not. By the way, if you have questions, please feel free to do so. Yeah, so here a few words about SEA. As I said, that's kind of the most used method. Most big software companies have an SEA solver in their toolbox. So what you're doing is you may have a structure like that. Here's a car, and then you take the substructure. That's it. The windshield could be one substructure, but it's the whole windshield. The roof could be one. The frame down there, and then maybe various beams. So the substructures are relatively small compared, if you compare it with the degrees of freedom you get from a fine element mesh. So that's normally, a couple of hundreds, maybe thousands, but not more than that. The idea of what you do is essentially you treat all these substructure as a reservoir where this energy is stored and sloshing around, and then there are various sort of exits or entrances where this energy can then flow out, and it only makes sense to talk about these substructures if you assume that you get some sort of equilibrium distribution in each substructure, and then you have some coupling. So the time it takes to equilibrate in each subsystem is fairly short compared with the time it takes to move on. So then you can do this kind of power balance method, and then essentially, you lose all information about the actual structure, about the geometry. The only thing you need is kind of the volume or the area of that, and you get very simple sort of graph-like structures where you have, various coefficients. Theta is this coupling loss factor. You have, it becomes something like that. The problem is, of course, that often these assumptions are not fulfilled, or you have to choose your subsystems very carefully in order for them to be fulfilled. And a big problem for the SEA people is, for example, the lower part of the frame, which is essentially one big, metal sheet. So it's difficult to substructure that. That would be. Do we have a laser pointer or something? No.
I don't think we do actually.
Or a stick. Or
You kind of did with the mouse, but
maybe I can use the mouse. Yes.
Yeah.
So essentially, here this bottom part, that is then one big substructure which stretches over the whole structure. You get then one value, one energy value for that, and that's always, that doesn't really make sense. So anyway, but this is used, and it can be used, and there are such justifications when it can be used. They're quite nice. If you think of this in terms of rays, which I will do in a minute, what you need is some sort of ray chaos in each of these subsystems, and you can justify that SEA assumptions quite nicely. Which, is normally not done. It's kind of a trial and error. Right, so what I want to do is go to ray tracing, and we will try to do ray tracing on structures. And let's, just start with the usual way. You have a source here, and you have a receiver point. You have the rays going from the source to the receiver. As a semi-classical physicist, I would write this down in terms of the Green's function, which essentially, just the energy or the rays going from this receiver point to the point R. It depends on frequency. You can write this as a sum of all paths going from this source point to the receiver point. You have some weighting here, and then you have here something like the length, and K would be your wave number. So that's, you can always write this down. This is already a high frequency approximation to some extent. But of course, there's a lot of information in there, especially there's all the path length in there. And that's what you would do by standard ray tracing analysis. You would try to find all these rays, then measure the lengths. You can of course also put time in, so then you get the time-dependent signal. But there's a lot of interference terms still in this approximation. So you get interference. You can also mimic resonances with that. You have to take care of the complexity of the geometry, of course. The big problem is what's normally the path sampling problem. So if you want to go to many reflections, the number of rays grows exponentially often, most of the time. And you also have this, that you may not sample this uniformly. So you get good results in some regions, but maybe not so good results in other regions. And the main thing is the complexity of the geometry in general. So to describe that, even in room acoustics, you all know that you start to simplify your geometry just because you have so many cases to consider. Just in this room here, every corner which is slightly different, you would need to treat extra. The question is now, how would you do something like this if you're looking at a car or an airplane? Well, again, of course, you have waves traveling in the structure. It's the elastic waves, but the structure itself is much more complex. So, do is essentially looking at the energy density of our structure. So here we are back to this picture where we have rays going from R0 to R. There can be many of these rays. They all have phases attached to it. But if you go to the square, you get kind of a double sum over these terms, which you had in this Green's function earlier. And then you can argue that the dominant term in this is when Lj equals minus, so when J equals J prime. And then you have as a dominant term essentially with something which you can interpret as the energy density. And then, in addition, you have interference terms. Sometimes this is referred to as the diagonal approximation, which is the dominant term. But here, of course, you have not lost all phase information. So the phase information is in these terms, in these interference terms in there. But you could argue that this is sort of an average value, and then you have some fluctuation on top, which are given by these interference terms. So we will try to only mimic or only model that part here, forget about the interference. By doing so, of course, we lose all information about resonances. We just get, we are back to a classical picture of energy flowing in that structure. Yeah? So there are no interference, no diffraction, nothing of that. That's all gone at that point of the approximation. So in the following, I will now look at this energy density, and it may depend on two parameters. R0 would be kind of a source point, and R would again be the energy density at some other point, which you get from this kind of ray tracing picture. And I will argue that what we're actually doing is we're looking at something else. We're looking at here a phase-based density. So instead of actually looking at this energy density, I'm looking at a quantity which is sort of more involved than that. It is if I want to sort of classify the rays, I need some directionality, and I can also say equally like I could say, okay, I take my source and I'm looking at all rays going out from that source and being reflected, and I describe them in terms of a phase-based density. Phase-based density meaning a density of the density of rays at a given point going in a certain direction. Yeah? So that's what I call phase-based here. I take the directionality as a separate variable, which I'm keeping track of. If you then integrate over this directionality, so k, which is reminiscent of the wave number vector, I call here my direction or momentum variable. If I then integrate over all direction at a given point, then I'm back to my energy density. Now, if I have that, I've doubled my variables by doing that. I'm looking not at the energy density itself, but I'm looking at this quantity which also knows about directionality. But the good thing is I can describe this in terms of a linear operator, sometimes called the Liouville flow or the Frobenius-Perron operator, acting on these densities, and that can be written down in a linear form. Essentially, what is kind of a pullback. So you have your density initially. If you want your density at a later stage here, this rho t x is my new double, twice as much my phase-based variable. So it has the position, it has a momentum. And if I want the density at some later time, I'm essentially pulling back the flow. So here's 5 tau, that's my flow. So that's telling me that the ray starting at a given point, going in a certain direction, 5t tells me where it is, 5 tau, time tau later. So you can write this down. You can also write this down in terms of first order differential equations. You know, these are these other equations. You know, that's back to differential equations. The first are quite deep, but that's, you know, that's where we are. Of course, the price you're paying is that you have doubled the number. What's time? What do you mean? Time is that, you know, you start. So essentially, it tells you when you start here. I mean, the time is sort of relative because it depends on what kind of, you know, velocity you're having at the end. You know, there's sort of this relation between frequency and momentum. There would be some sort of wave velocity which you could use as your variable defining time. But in essence, it's a parameterization of that curve which is sort of going around here. You just do that, yeah, consistently for all rates. I will throw out time straight away because I don't like that. So what we were thinking is that if that's a way to describe my energy in on the structure, how will I implement that? This operator is difficult. You pinpointed it right away. You know, if you're looking at really doing this in some sort of fictitious time here, then you know you would need to track all rays again all the time. And you know, if we wanted that at a specific time, you know, the rays can end up at many different positions in that structure. So what we are thinking is that what we're describing here, yeah, we are already in the frequency domain. I haven't, everything I told you here was in the frequency domain, and then, you know, I'm boiling it down to this kind of ray equation. So if we're in the frequency domain, we are actually describing something where we have a point source, and it sends out energy all the time, yeah? And eventually you have an equilibrium of the structure. So, you know, your structure vibrates in some parts different than others, because maybe there's some damping in there. But otherwise, you know, you get an equilibrium distribution, and that's the kind of equilibrium distribution we want to describe. So the idea is, I'm doing that slightly differently. I'm actually describing that as a map. And then we very easily come to meshes. So think of this being our system here, but then later on it will be a mesh cell of a much larger mesh. And think about, you know, you have this source in the middle. So what you can do is you can essentially see how this energy now goes to the boundary, and then once you know what the energy density is on the boundary, you can then map back from boundary to boundary, and you get a boundary map. Yeah? That will also describe your equilibrium distribution, but the nice thing is you have sort of thrown out time, and you have now a geometric description of that flow in terms of maps from boundary to boundary. So the idea is to describe this internal source as, you know, you could think of this as kind of a light source, and you replace that by what's reflected here by the mirrors at the boundaries. And that, of course, gives the same thing after you sort of excluded the direct path. And then once I have this source on the boundary, what I'm doing now, I'm just mapping my source on the boundary back to the, you know, to the other boundaries. And I describe this as a boundary map. So the boundary map is now, instead of this continuous flow, I'm just looking at something which maps my coordinates S and PS being the direction tangential to the boundary. I map that, you know, where it sort of ends up after one reflections. And now I can use that map to map my phase-space density, but now it's a phase-space density in a kind of concrete surface section plot, or, you know, in some reduced plot that got rid of time and also get rid of one of the variables. So that's sort of what we're doing. Now, so instead of having only one of these sort of regions here, I can do this and add another cell here and another cell. And again, I just, you know, I start with boundary density, and now from then on, you know, if it is just going through, then I can now map that to the boundary of the next cell, the boundary of the next cell, and so on. So that's sort of now an implementation. That's all I want to say about the method. That's now an implementation. I'm not sure whether you can see that. So there's a mesh in this purple region, and there's a source coming here from one of the boundaries. It's a quite directed source. I can choose my source wherever. But think of that sort of, as an excitation. So somebody banged there on the structure, and this thing is now propagating. Oh, right. That happens when you copy. So this red square is actually rho. So rho naught standing for my initial excitation or initial energy density. T is now my operator, which maps these functions, these density functions, from one boundary to the next. And now you see sort of what's happening here. You're sort of propagating this slowly through the structure. You have some numerical diffusion here. Oops, sorry. Because when we actually construct a map, we need, you only have a finite resolution. You get infinite resolution only if you have an infinite large map, because it's an operator. But for finite resolution, you have a certain dispersion here. But T is a matrix, it's a linear operator, and of course, in any approximation we choose, it's just a matrix. Right. So here's the kind of equation we solve. So think of a rectangle thing rho. So what you do is, if you now want to include all the reflections, what you do is you just propagate this further and further and further, and eventually you get reflections in and so on. And if you now take the number of iterations of your operator acting on your initial density to infinity, you're getting some equation like that. So you have a simple equation that the equilibrium density you're looking for is essentially given by 1 minus T inverse your initial density. So we can do that on a mesh. We need to define some sort of basis functions, or some way of describing the function on each of these boundaries. But there are various ways that we can think about that. And here's sort of another example. That's again a part of a car. I think that's where the wheels are and various things. The excitation was assumed to be here. You don't see the mesh itself, but there is an underlying mesh. We usually use just the finite element meshes we get from people who are interested in that. So we're quite good now in rewriting finite element meshes in the kind of meshes we need. They're slightly different. And then here we have some damping in. That's why sort of it's going down. You see how this energy density is sort of moving through the structure, and you get more or less what you expect. The further away you are from the source, the less intensity you have. But there are various sort of details which you might not guess, because a lot of energy is just going here up into this upper part. Now you might ask, okay, how big is the problem? The problem is as big as the mesh. So for every mesh cell, we typically, if it's triangles, we have three sides. So it's 3 times the number of mesh cells, because each side is treated as sort of a, where our boundary densities are defined. And then of course, you have also, you need to resolve the directionality of your arrays. So you have to multiply this by the number of basis functions you want to use to resolve your directionality. So that is typically 10 basis functions is good enough for that. So you get about 30 times the number of mesh cells you need to set up this T matrix. So these are big matrices, but they don't scale with the frequency. Yeah? So we can take a mesh which is maybe done for 100 hertz. They're not too big then, but they describe the structure already quite well, and we can scale that up to kilohertz. Yeah? Where normally for a structure like that, you would probably need a couple of million mesh cells. So we are quite used to having mesh cells. Sure.
And how do you choose the cells? The size of a cell?
The size of the cell is determined by whatever frequency range you wanted to look at. So typically you say 6 points per wavelength. So if that is if that is a mesh done for maybe 100 hertz, then you go back to the kind of material you have, and then you know how large the mesh size
And
is.
then this matrix should depend on the density.
This, for us, we can take
The size of the
yeah. So the size of the matrix, maybe it's down to 100 Hertz, maybe it has 20,000 elements in there. Yeah. We take that matrix, but now do calculations. You know, in FEM you could only do a calculation up to 100 Hertz. Yeah. In our method, we can do the same calculation up to kilohertz. Now you ask me, okay, where's the frequency coming in?
Yeah.
The frequency is not coming in into the energy flow. That will show you in a minute. There's certain elements, for example, scattering matrices, which will still include in that, which have a slight frequency dependence. But I have to stress, you know, what we get is sort of very boring curves telling us, you know, there's no resonances in there, so we get very boring curves telling us, you know, how things are sort of smoothly changing with energy for these structures.
Can I ask one more
Sure.
question? What if you go back and make those cells as large as the elements initially in the statistical thing you showed us? Will you recover the same result as the statistical?
So we can essentially, I mean, it sort of doesn't make sense. We can do that, of course, as well. Yeah. Then we assume that that's essentially only one energy value for the whole substructure. You can argue that, in essence, the method we are having, or SEA is a very low resolution approximation of the method we are having. Yeah. So if I'm choosing here, for example, no base, or just the basic basis function for the directionality, which tells kind of a Lambda law type of thing. So every ray coming in is kind of scattered in all directions. Yeah? That would mean that's the lowest order resolution you can have. Yeah? That's what you do in SEA. Yeah, we can then, of course, in this case, we could then take the SEA subsystems and choose sort of the whole boundary as one of our boundaries, and no resolution in directionality, and we're back to something which is very similar to SEA. Point. Now, lots of nice pictures, and these are the equations already. Oh, they're copies, but you know, these are just definitions. So, so what I told you is, if I want the energy density, so we get the phase-space density. So I can tell you at every point how many rays are coming into that point, in which direction they're going. Yeah? And I interpret this kind of as energy fluxes. As I told you, most of the time you're only interested in the energy density, which is something like, you know, the mean amplitude of your excitation. So that gives you some idea how big the amplitude is at that place. Then you integrate out the direction variable. So you're only interested now how many rays come in, but you're not interested in which direction they're going or where they're coming from. That gives you the energy density, and that's typically this color scale I'm showing there. Yeah? So here it's another car part. Here's the excitation, sort of at the bottom. You see that, you know, from the excitation, the things sort of move out. So that goes from red to blue. But we can also do something. We have more information. Yeah? If you do that, you're throwing out a lot of information you have. I mean, all the directionality is gone now. But what we can also do is we can sort of compute the mean intensity. Right? So essentially, we know how many rays come out, sort of go out this way. We know how many rays go out that way. So essentially, if we average over these rays with the energy or phase-space density, then we get some information about how much energy is actually flowing on average in a certain direction. And that's kind of the picture here. So these rays give us some indication where things are flowing. Here it's quite simple. Everything's sort of flowing away from the source. But I will show you a couple of pictures later where this is you know, a bit more. There's more information. We call that the energy flow map. But essentially we can measure the intensity with that. So here is the definition. It's a vectorial quantity because we average here over the direction variable with this density, phase-space density we have computed. This row is the outcome of our computation. Yeah? So this is kind of a post-processing step, which you're doing. something, maybe I should speed up because I want to go to turbulence boundary layer. What I briefly alluded to is, let's assume you have a structure like that. Again, that it's a structure which was given to us. It's a kind of a plate, and then there are all these other plates in between. They can be quite large. It comes from these double walls from ship tankers. And in this case, you have now interfaces between plates. So you have one plate here, the other plate here. And of course, what happens there is there's reflection and transmission, but there's also mode conversion. So you can actually mode convert from a flexural mode into a longitudinal shear mode. So what you can have at these interfaces is indicated here. So let's assume you have a flexural mode being excited, but whenever this ray hits the boundary, it can now be mode converted, but it can also now be scattered in various directions. Okay, we take that into account, so that's included in the software. You get the pictures like that. So that would be, bending, or maybe we start with this picture here. So bending wave is coming in, and then there are the various other wave types which are now transmitted or reflected from this plate 1. And here you have an example how this can look like. So as a function of the incoming angle of the bending mode, you get all these different wave types. So here's, this blue line is bending from plate 1 to plate 1. Here you have bending pressure, but you go from plate 1 to plate 2, and so on. What we have implemented there is essentially a simplified version of this paper by Lange and Heron from 1990s. We make a certain approximation with the line junction approximation, but then you can do that. Yeah, and it's simple matrices. I mean, in this case, it's a 10 by 10 matrix or 9 by 9 matrix, but you still can compute that. You put that into the software. So whenever your ray now hits a boundary, I'm checking, how many junctions are there, and then I give a sort of probability of whether I'm reflected or transmitted or mode converted. And that's sort of an example here with, again, completely finite element meshes. All right, I thought I'd show you a couple of things because that was an exciting time. So essentially with Yanmar, they paid us money for validating our method. Of course, they used it then later on. I'll show you an example where they used it. So application was this Yanmar tractor. So this is the tractor itself. I've seen it. We went there and visited. I'm not sure what it is. This is sort of the front frame. That's where the engine, where the gearboxes would be sitting. And here you have the cabin, with glass and the seat and so on. They were interested for. They wanted us to model the sound pressure level at the driver's ear position, so quite a challenge, but they made it slightly simpler for us because the engine wasn't included. So essentially, it was just this frame here. So it's all metal apart from these windows. So they measured that. So the critical point was here, this mount, so where the frame is connected to the cabin. So that caused some problems, so that's why I'm pointing this out here. That is, of course, in there to isolate the cabin from the structure. They did various measurements. So they excited it at some point. I think here at the back, and these were accelerometers all over the structure where they did measurements. We did the computation with our DA program, which we had at the time. So the excitation is down here. You see that there's some decoupling happening. So we saw that in our calculation as well. And you see that most is sort of stored in here. Some of the energy sort of travels along this frame, and then some actually also travels in the cabin. Here you see sort of the interior of the cabin. So we predicted that most of the energy will actually go here for these fenders and through the bottom. Okay. They wanted the results, and before they showed us the measurements, which is always nerve-wracking. But at the end, it wasn't so bad. Our first result was this. So these are various positions where these accelerometers are sitting at a specific frequency, 200 Hertz, which is quite high. So the first result was this red curve, and they were quite happy about that. So that was a relief. So we sort of, got the fact that it's dipping down here. I think that is the frame. This is mostly the cabin. We noticed that the main problem we're having is that we don't really know what these damper mounts do. So we sort of adjusted that, and we got this sort of black curve where we sort of taking care of. There's some sort of frequency dependence of this rubber mount as well, and so on and so forth. And it gets to the dirty details. That's always the problems. Your model is only as good as the parameters you get. These are some of these intensity maps. So, and they're really like that. Now you clearly see that sort of a lot of sloshing around, and the energy is going back where the excitation is. But then you also see how energy actually moves in here, and how it sort of travels up. And we predict here that the front gets much more energy than the rear. So now you can look at where this energy is actually entering the cabin, and then you can start making modifications which hopefully will prevent that. And that's what they did with a different model, and we weren't even involved in that. They did the calculations. That's another picture of this intensity map, just in this case not only the errors. And I said, we're most interested in the excitation of the cabin actually. So that's why they did that. They did some more detail. I don't want to go into much detail, but they did this without us. So they have the software, and they wanted to understand. They realized that a lot of energy goes over these fenders, so they tried to understand where it's actually entering the fenders. And they did this with our software, and then they identified there's a sort of point where things are actually coming in. Here's sort of more detail of that. Then they decided, okay, maybe if you do an impedance match at that point, so here's sort of one plate and there's a second plate, and that seems where most of the energy is flowing in. If you make one plate thicker than the other, then more will be reflected. So they tried that out again with our software. I'm not sure whether they built it, and they saw a slight improvement here in making this modification. So that was nice. As I said, unfortunately, Satoshi Morita has left the company, and so since then it's a bit dormant. That's always the problem with these industry applications. All right. This is sort of my take on DEA. You have questions on that? Yeah.
So apart from looking at experiments and comparing, do you have the mathematical ideas on how to estimate the error that you make by your approximation?
We had a collaboration with Primary. There's sort of the people on transfer operators are sitting there. We got them interested. They needed some convincing, but we got some money for that. We have some ideas now about that. So the tricky bit is with these kind of operators, it depends very sensitively on the function spaces you're looking at. Yeah? So the question we were looking at, we were, for example, using Legendre polynomials to resolve our directionality, and they were sort of questioning whether that's necessary. Maybe you can use piecewise constant. It's as good. So essentially, we have now some insight that, probably piecewise constant is the best you can do, and you have then linear convergence in that function space. And you can't get any better than that.
By linear convergence, you mean according to what parameter?
In
finite element, you really
it's in the size 1 over the size of the model.
So it's because so it is somehow. You see what I mean? Because when you increase your frequency for a given model, do you also increase the error or not? Because this is the
it's not frequency dependent. The conversions. It's just how good you are resolving your phase space. So we always. So for example, if I use piecewise constant functions on the boundary, then of course that is an approximation of the true thing, and the same by resolving the directionality. So essentially, what the outcome of that was that there's something which is called the Euler map. Sorry, not the Euler map. The Euler method of approximating these Frobenius-Perron operators. And there, the idea is you take everything just piecewise constant, both in momentum space and position space. And you get this sort of convergence you get through this Ullum.
But I still don't see, what do you, if you have a result, you want it better, what do you reduce or increase in your parameters?
I increase, is there a pen?
I've got one back.
Oh, thank you.
Thank you, external visitor. Various colours.
So if you have your mesh, yeah, and that could be one mesh cell, yeah, I can assume, my basis functions could be piecewise constant. I'm assuming that the solution, the density here is, constant on that part here. That's an approximation. If I want to refine that, I sort of, make it piecewise constant on subdivisions of that boundary. Yeah. By doing that, of course, I increase the size of my matrix. And that's sort of, that's exactly what we do.
So the number of points per edge of your mesh is a parameter that you can play with.
And then in similar, what you're actually doing is you have here sort of your X space, right? That's sort of X. Okay? Then you have here your P space, that's sort of resolving the directionality here. And now what you have to do is, this is not just a one-dimensional line, it's a two-dimensional space, which you approximate. So what we typically do that gives nice smooth pictures, we resolve the P space in Legendre polynomials, but of course only a finite number. But in essence, you could do the same thing, and that's what David Chappell's preferred method is. He just says, I'm only sending out rays in certain discrete directions, and then increase the number of possible directions.
So you're into the picture, the quadrature for your integer.
And how is that related to making the cell smaller? If you have piecewise constant.
I could, in addition, instead of subdividing each mesh cell, I could, of course, subdivide the cell itself, and by doing that, I get more boundaries. Yeah. So I essentially, instead of having 3 boundaries here, I have now many more. So again, I would have let's assume we stay in the picture where we use piecewise constant, but now I'm piecewise constant only on that part, and I can have a different value here. So again, I'm start resolving the actual function which sits on that boundary better and better. Typically, we don't remesh because that's a lot of work. If you want to do that properly, then you would need to go back to the CAD model you have, and then remesh that, which is expensive. We don't have the software for that. Of course, you could just take whatever mesh you have and subdivide it in some way without taking care of that there's curvature involved. But again, that's work, so we don't do that. So typically, we subdivide each length. How are we doing time?
Got about 10 minutes.
10 minutes, okay, that's probably. So something we got involved in a project called Silent Prop. They think about how could we do electrified aircrafts? And one of the questions they had is, how can you make them more silent? And one of the questions they had is, if you have lots of propellers now on your wing, that will excite the structure. Can we predict that? And then we came in with our software and said, yeah, we can do that. But then, of course, in the discussions, it turned out that maybe the problem which really produces noise is the turbulent boundary layer. Yeah? So that got me thinking, okay, maybe I should think about this a bit more, and we made a PhD project out of this. Joshua Finn is on that. The problem for us is now that if you have a turbulent boundary layer exciting your structure, then the source is everywhere. Yeah? So far, I've always assumed the source is kind of pointwise, and it goes out of, it could be several independent points. That's easy, but here we're talking about extended sources and actually correlated sources. Yeah? So there is some correlation. If you have a certain excitation at one point, you most likely have some excitation of a similar range on the other. And of course, correlated sources is very interesting. I came across that if you have a sort of an electric engine, something is rotating in there, the noise will also be correlated. There are various points where noise is created, but it's actually correlated across sort of this circumference. And so far we assume that all sources are uncorrelated, so we can take them independently and just sum the results up. For correlated sources, that's different. So I thought that's an interesting thing, and Josh got working on that. So the idea is you have a turbulent boundary layer. Turbulent boundary layer forms as some air flows over the structure. It needs some time to build up, of course, but let's assume it's fully formed turbulence. It has typical pressure fluctuations, which are often described in terms of correlation functions. A model which is often used is probably not the best model. We have looked at other models, and that's not too difficult to do. Is this Caucus model where you assume these are sort of just exponentials, and maybe we should explain that a little bit. So these alpha x and alpha z are some parameters which depend on the structure. Kc is related to the flow speed, how fast the airplane is flying or how fast the air is going over your structure. And this psi x and psi z, these are essentially now my length scales. X along the flow, now the airflow I'm thinking that, and z is sort of perpendicular to that flow. The y direction would be perpendicular to the structure, which I only need to take into account if I want to describe the thickness of the turbulent boundary layer. But this is sort of now this doesn't appear in this model. So it depends on two parameters, R1, R2, which essentially, which is encoded in here. Psi x is some sort of R1 minus R2 in the x direction, and psi z is R1 minus R2 in the z direction. Yeah, so a very simple model, and as I said, that's maybe naive, but anyway, it's a challenge already, and once you understand that, you can do other models as well. Oops, sorry. All right, let's just put this all up. Okay. So what we want to do is what I just described. You want to now simulate this. You want to simulate the vibrational response. Yeah? You're not interested in the turbulent boundary layer itself. That's given. But now the turbulent boundary layer excites every point, and then what happens with this excitation? Is that actually moving, or is that just staying there? Is that homogeneous? Is it not homogeneous? That was the question we wanted to look at. So the turbulent boundary layer we assume as homogeneous. The simplest model we can make is sort of just looking at a plate. So there's a turbulent flow across a plate, and there's an experiment quite recently, which looked at this in detail from Machete et al. That's the group in Canada. What's that again? Laurent Marcy was involved, and some other people, and Barry, Chevron, yeah. So they have this lab here, very nice. You have that as well, I suppose. You could do the experiment if you wanted. So they have put this plate in here. Here's the flow coming in, the airflow. There's sort of various things to make it turbulent, and then you measure that, the excitation of that plate, and you also measure the turbulent boundary layer across that plate. Typical flow speeds in the experiment are between 20 meters per second up to 40 meters per second. In our simulations, of course, we can go higher. We've done all the way up to 300 meters per second, which is, it's a very fast plane, but you can of course do that. You may have various damping coefficients in your structure, in the structure now. So we excite the structure. We're very interested in what's happening in the structure, not what's happening with the flow. How would you do that? So you have only the correlation functions of the excitation. Did I put that here? Sorry, no. The idea how you can do that is. Here you have your correlation function, this gamma which I showed earlier. We make a transformation to some sort of mean variable and distance variable, and then we go to something which is called a Wigner transform. So now we do a transform of that type. It's kind of a half Fourier transform. So you do a Fourier transform only in this distance variable here, but you take it at half point of your function. That is called Wigner functions. It's very well known in quantum mechanics. That's where it comes from. Wigner was, of course, very involved in that. And that's, in quantum mechanics, one sees it as, you know, you have your wave function. You can write this as a density operator. But if you want to sort of, you know, go to the classical limit, you want to get to something where you have position and velocity. So that's essentially a transformation which gets here from your density operator to a function which now depends on R and P. So that is now a function which is defined in phase space. And it turns out that makes absolute sense if you have a correlation function. The source we are looking at, the source of our ray excitation, is the Wigner transform of that correlation function. So what we're doing is we take this correlation function, which is given, it could be any correlation function, we make this transform here, and then we do the Wigner transform of that, and it has this kind of Lorentzian type shape. The interesting thing is that the Wigner function itself is not uniform. So it's not like lots of point sources where at every point it goes out in all directions. It has preferred directions. The Wigner function tells us that the structural dynamic, the energy flow in the structure has a preferred direction, which is along the flow. And that's so this is plotted here. So now we have here our structure again. This will be our dA calculation. But the source we're inputting at every point has a preferred direction to go along the flow. This is the flow, airflow. So that's telling you how much energy density is flowing in that particular direction. Yeah? And you see that it goes with the flow. It depends also on the speed. So as faster you go, the more of your energy wants to flow in the structure. We're not talking about the airflow. We're talking about the structural vibration having a preference to actually move with the flow. I'm not sure whether that anybody has sort of considered that. Of course, if you put that into our dA, what you see is that even though all parts of the plate are excited in the same way, but once it's excited, it likes to go with the flow. So you must have more excitation at the rear end of the wing than at the what's it called? I'm not an leading edge. Sorry, leading edge, trailing edge, exactly. Yeah? So you must have more excitation at the leading edge. And the vibrations must be larger there than at the trailing edge. Just assuming that picture. And that's here we implemented that. So here it's just implemented for one cell. So we assume here that the turbulent boundary layer only excites that cell just to see what's happening. And you see exactly that. So essentially the cell is uniformly excited, but the energy actually flows predominantly in this direction of the flow in that structure. That's it, yeah. So just for an example, let's assume we can only excite one cell with the turbulent boundary layer. What you see is then there's the preferred direction. Try to do this for a plate, and indeed you see exactly the same thing. So you have an excitation of the plate, but you see there's no color scale. Yeah, I'll show you some examples later. But essentially, again, you see that on the leading edge of the plate, there's less energy than at the trailing edge. And you can do this here. This is for different velocities. So this is a very low velocity. Oh, sorry, the flow direction has changed now. Now the flow goes in the other direction, sorry for that. But you see that as you increase the flow speed, this directionality becomes more pronounced. And yeah, and that's what we try to figure out whether this can be seen. And it depends a bit on the damping. If the wing is highly damped, then essentially a lot gets lost. And then the effect is sort of relatively larger. So that's sort of what's shown here. So you typically get, now the flow is going from right to left. You typically get that you have more energy here than here, but the energy difference is not so big. Yeah? But then if you make damping larger, then essentially the whole thing goes down, and relative the energy density percentage difference then can go up to something like 10, 12%. So, the question is that measurable? I don't know. I find it's an amusing thing. It doesn't seem anybody has noticed that, so didn't appear in any experiments. But you know, what we're predicting is that a turbulent boundary layer tends to have energy which is flowing with the flow in the structure. So the excitation in the trailing edge should be larger than the leading edge. As I said, you know, maybe at certain wave speeds that could be measured. You probably need that is relatively large damp, and it could be an effect which is, you know, in the 10–20% range. Which, you know, given that you have lots of fluctuations on top of that because you have a statistical model for the excitation, not clear whether that's enough to be measurable. All right, I'll leave it at that. So I want you what I want you to take away is that here is a mesh-based simulation tool which you can use for modeling vibrational energy density on fairly complex structures. We have validated it, and we have also looked at correlated sources. That's what I showed you. What I haven't shown you is that we also looked at how you know, we have implementation for also tropic materials. The dispersion curve is non-trivial, and you have to think about how your ray dynamics is compared to, you know, yeah. So it's no longer isotropic. Rays again have a potential direction. We have looked at sound vibration from plates. Again, you have to think about, we have thrown out phase. Yeah. So in DA we have no, yeah, we have a little bit of phase information, but we don't have phase information. If you look at sort of standard theory for radiation of plates, you have something like Rayleigh integral. Rayleigh integral, of course, needs phase. Yeah? So, you know, you couldn't get anything like critical frequency if you don't have phase information. We found a way to get the phase in, essentially. And it's sort of the inverse thing. Instead, we start with our phase space density and now do an inverse linear transform, and that gets us a correlation function. So we can use that to then predict sound radiation from plates. And we have a 3D extension built for which you could in principle use for acoustic or electromagnetic waves. It's very slow. All right, I'll leave it at that. Thank you.